on chapter 1, and the game plan here for lab is we'll do some lecturing because we kind of took up pretty much all the time there. I'm talking about the syllabus and the class. We'll do some lecturing, we'll stop. We'll also talk more specifically about some things here in lab, and then that'll probably wrap it up here for today, I think. But before we do sort of start off here in lecturing, is there any questions anybody sort of had about the class or anything like that that we talked about earlier that I could sort of address before we start lecturing? And again, just like before, if you have a question, feel free to chat it to me, or if you would like to unmute yourself, you can do that as well. Okay, and obviously that goes for as we're lecturing as well. A reminder, as I mentioned earlier, the way the book is really orchestrated, and by the way, that the cover there may not be the correct cover for the second edition. I think that might be the first edition as a cover, but just so you know. I think the second edition, I almost want to say it's reddish pink, maybe. So the way the book is set up and the way we sort of lecture here is, as I mentioned, we really do start with the atom. We talk about the atom, sort of the experiments that led to the understanding of the atom, the structure of the atom. We get into then sort of protons, electrons, neutrons. We get into then in the next chapter, electrons, electron configuration, waves, and that type of stuff. So traditionally in a class, for example, in the 100 class, you probably got to this topics midway towards the end of the semester, but here we sort of started with these guys, this sort of topic, and kind of work our way backwards to things like moles, grams, nomenclature, and that type of stuff. So we'll start here with chapter 1, and it is about chemical foundations. And really the majority of this chapter will deal with really the atom, and as I mentioned, sort of the discovery of the atom and sort of what led to our understanding of the atom and the different parts of the atom. So first off, when we talk about chemistry, we oftentimes want to understand really the connection to sort of what we see in the sort of big picture, if you will, the macroscopic sort of world, to what's happening really on the level of atoms and molecules. And what we really deal with a lot is the idea of, on the atomic level, what's happening with atoms, molecules, what's happening with electrons. A lot of what we deal with in chemistry involves really electrons being involved. Not very much in terms of neutrons and protons and things like that, but electrons are really the basis of bonding, the different types of bonds that we have. They're also, because in most chemical reactions, what occurs is basically those bonds break. So we're talking really about sort of electrons either sometimes being transferred, sometimes being shared, breaking apart bonds and making new bonds. Other major sort of things that we talk about, and I won't say so much in this class because they kind of took it out of this class, is energy and heat and what's going on in terms of reactions and what's going on in terms of, is that giving off energy? Is that absorbing energy and stuff like that? But really a lot of what we deal with has to do with basically matter. And matter really is pretty much anything that occupies space and has mass. So matter is pretty much anything that occupies space and has mass. And when we talk about matter, there's really three sort of phases of matter, if you will, that we deal with a lot in chemistry, and that is solid, liquid, and gas. And a number of what we deal with involves really the transition of going from those different phases, going from solid to liquid to gas. So when we think about things in the solid phase, things in the solid phase are typically, packed in there pretty tight to each other. There's not a lot of room for movement, and that's why they're typically rigid. They're very hard to sort of change the shape of it. And that's typically what we see sort of in the solid state. And that's a little bit different than what we see in the liquid state. In the liquid state, everybody's still relatively close to one another, but they do have a little bit more room for movement. And when we think about liquids, liquids are fluid. So they have really enough energy to sort of pass each other. And that's why, again, in the liquid phase, we see that sort of like water and stuff like that, that flows obviously like a liquid. They're able to sort of move past each other. Solids really don't flow, right? They're like bricks. They just drop basically. But you pour water, you can definitely see it, as opposed to if you took an ice cube and you dropped it, right? It just goes as a whole unit. Now, when we get to the last sort of phases of matter, which is the gas phase, that's the phase where everybody has basically completely broken apart from one another. So they're flying around, they're banging into the walls of the container. As we'll talk about, that's basically what we associate pressure with, right? When we talk about gases, we talk about gases and pressure associated with it. And that occurs as they are basically flying around and colliding with things. The other kind of important things in chemistry that we deal with is those transitions. So when we go from solid to liquid, that is the transition known as melting. When we go from liquid back to solid, that is the process known as freezing, right? If we go from liquid to gas, that is the process of evaporation or vaporization. And if we go from gas back to liquid, that is the process of condensation. We could also do a process, as you may be familiar with, going from solid directly to gas, sort of skipping the whole liquid part of it. And that is what is referred to as sublimation. And lastly, we could go from gas, again, skipping liquid, going back to solid. And that is what is known as condensation. So these sort of transitions that occur, it's a lot of what we see in chemistry. It's a lot of what we deal with sort of in chemistry. Other important things, about this, and again, some of this you might be familiar with, but when we talk about sort of these processes here, this melting and freezing, they do occur at the same temperature. So at 0 degrees Celsius is, for example, water where it freezes. It's also where it melts. And exactly at 0 degrees Celsius, as we'll talk about in a later chapter, that is where we have kind of both phases in what's referred to as being equilibrium with each other. There's basically solid and liquid occurring at the same time. It's not, for example, in terms of water, that when you go above 0 degrees, that you really do get liquid water. If you go below 0 degrees, you get basically ice. But exactly at 0 degrees, you basically have both things occurring at once. And that's the normal, usually melting point temperature or freezing point temperature. And the same thing occurs over here when we talk about sort of evaporation and condensation. These guys also occur at the same temperature. And that, for example, is 100 degrees Celsius if we're talking about water. At 100 degrees Celsius, that's when water boils. That's what's known as the normal boiling point of water. And the same thing actually occurs at 100 degrees Celsius. You basically have both phases in equilibrium with each other. You have some liquid there, you have some gas there. It's not until you get really above 100 degrees Celsius, when we're talking about water, that you do kind of go into the gas phase. Below 100 degrees, you're again into the liquid phase. So what determines sort of which way you're going to go, right? Are you going to go melting? Are you going to go freezing? What determines that is really energy. And so what is happening with energy? And typically when we go, for example, from solid to liquid to gas, if you think about just the example for an ice cube, right? If you take an ice cube, you take it out, it basically picks up some heat and energy from the surroundings, and it starts to melt. You take the liquid water, you put it on the stove, you light some fire underneath it, right? And you heat it up like you're going to make some pasta. That then makes steam, right? As you're boiling that water. And all that is what is referred to as being a endothermic process. And endothermic process in terms of heat and energy means that heat is absorbed. In this case, the ice cube, for example, keeps absorbing, or the water basically keeps absorbing the energy. And as it does, as it gains energy here in the solid form, these guys are able to kind of move away from each other. They're able to kind of start passing each other and go into the liquid phase. And as you continuously heat it in the liquid phase, they gain enough energy for the individual water molecules to basically separate out from one another and really start flying around as gas molecules. Vice versa here, if we're kind of going from gas to liquid to solid, the opposite is sort of happening. This is what is referred to as an exothermic process. And that means that heat and energy is released. So again, if we started in the gas phase, as they lose that energy, what ends up happening is before they lose that energy, they're flying around really fast. As they lose that energy, they start flying around a lot slower. As they fly around slower, when they come in contact with other gas molecules, for example, they no longer have enough energy to basically escape each other. And they basically drop out of sort of the air, if you will, and they drop back into the liquid phase. If you continue to take out heat and energy, these liquid molecules, which had enough energy to sort of move past one another and become more fluid, now pretty much locks down into this more rigid arrangement that you have in the solid state. So a lot of what we deal with in chemistry does deal a lot with this sort of transition of these states. It also deals with the energy associated with it. But to be honest, we don't talk a lot about energy in this class. Again, if you take 200B, you'll talk more about the energy aspect of it. They sort of removed it from this course. I think it's chapter 6 in our book. But we will talk a little bit about energy. And by the way, there is a certain amount of energy really just to do the transition from, say, solid to liquid or liquid to gas. For example, we'll talk a little bit about it maybe along the way. The delta H of fusion is the energy required to do the transition of going from solid to liquid or liquid back to solid. Delta H is what is referred to as the enthalpy. It's kind of like the heat of a reaction. And when we talk about fusion, this occurs at 0 degrees Celsius for water. And for example, at 0 degrees Celsius, if you wanted to take ice at 0 degrees Celsius, which is essentially water in the solid phase, to liquid water at 0 degrees Celsius, not change the temperature or anything like that, but simply take it from solid form to liquid form at the exact same temperature. The delta H of fusion is the energy required to just do that process, not change the temperature. Changing the temperature and energy, and again, we don't really talk about it in this class anymore, but you might have talked about it in 100. That's what you use something like perhaps specific heat, if you remember specific heat, like Q equals ms delta T. You use that to figure out what happens when you change the temperature of a substance in the same phase. But here, the delta H of fusion is that energy required to do the transition from solid to liquid or going backwards. Same thing over here for evaporation and condensation. The delta H of vaporization is the energy needed to go from liquid to gas or gas back to liquid, basically. And again, same idea here. If we were talking about water, it would be at 100 degrees Celsius, simply taking it from liquid water at 100 degrees Celsius to basically gas at 100 degrees Celsius or steam at 100 degrees Celsius. And there's a certain amount of energy required to do that. Now, when we talk about energy and something that's good for us to sort of know, because we do come across it, because, well, your textbook thinks you learned that chapter, even though we skip it in this class. But delta H, again, is that sort of energy sort of equation that we sometimes see. If you see a delta H value that is positive, or even a Q value, if you remember Q is heat, that's positive. Those guys refer to usually an endothermic process, like heat and energy is being absorbed. If you see a delta H value that is negative, or a Q that is negative, and again, Q is heat, kind of from that specific heat equation, like Q is equal to ms delta T, Q is heat. That refers to an exothermic process. Again, heat and energy would be released in that particular case. Again, although we don't formally sort of lecture on sort of heat and energy and stuff like that, there are places along the sort of semester here that, you know, the book, and obviously we talk about it because, again, they kind of assume that you did that chapter, which is chapter 6, that they talk about delta H and those type of values. So for us, you know, if you just remember delta H or any type of heat value that is negative means exothermic. Any type of sort of heat value or energy value that's positive means that it's endothermic. You know, you'd be pretty sufficient for our purposes. And just to give you an idea in terms of, you know, in terms of these processes here that we're talking about, that which one would be require more energy. The delta H of fusion for water, this is for water, is roughly 333 joules per gram, while the delta H of vaporization for water is about 2260 joules per gram. Now, you can see that is about 7 times more energy. So it takes about 7 times more energy to do this transition than it does to do this transition. And it sort of makes sense if you think about it. As you go from solid to liquid, in the solid phase, everybody is still in there pretty tight to each other. When you go into the liquid phase, everybody is still relatively close to one another, but there is a little bit more room for movement and things moving around. But when you do the transition of going from liquid to gas, or backwards, from liquid to gas, you're going from a state where everybody's relatively still close to each other to a state where they have basically completely broken apart from one another. So it takes a lot more energy always to do the transition between liquid and gas than it does between, say, solid and liquid. Any questions on any of that there? So let's start talking about some of this sort of introductory stuff. So obviously matter, as we just talked about, they're basically composed of tiny particles, which are atoms. You know, atoms are basically the smallest unit that you could have for an element. It's like the basic building block, I guess, of an element. You know, if you say you have an iron, you would say you have like an iron atom, and that would be the basic part of it. Atoms, as we'll talk about definitely in this chapter and beyond as well, contain subatomic particles. They contain protons, right? They contain neutrons, and they contain electrons. And as we talked about, in a majority of all chemical reactions, it's pretty much these guys which are really, really important that's sort of happening. Now, a molecule is 2 or more atoms that are acting as an unit. So basically, a molecule is a combination of 2 or more atoms. Now, there are some terminology that sometimes people sort of get confused about the differences between them. So first off, let's talk about elements. Elements, you know, atoms are basically are the basic units of elements. You look on a periodic table, you can see all the elements. Sometimes elements come as diatomic molecules. Things like hydrogen, the way it naturally comes is as H2. Things like oxygen naturally come as O2, N2, F2, Cl2, Br2, I2. These are all elements, but they are also what are referred to as diatomic molecules, which means they are actually molecules. They are molecules because, for example, in hydrogen, there are two hydrogen atoms, right? One atom, two atoms that are bound together through sharing of electrons. Oxygen, there are two oxygen atoms that are bound together. Nitrogen, there are two nitrogen atoms that are bound together. Now, all these guys are molecules. They're all also elements. And the reason they are elements are because they contain basically the same atoms from the same element. Like hydrogen, there's two hydrogen atoms, two oxygen atoms, two nitrogen atoms. So first off, that is typically how these elements come. So if you said you have molecular hydrogen or molecular oxygen or just hydrogen and oxygen by itself, uncombined, it should always be H2, which is a gas. So hydrogen, oxygen, nitrogen, fluorine, chlorine, they're all gases. That's how they normally come. So these elements here are also really molecules because they meet the basic definition of a molecule, which means we basically have two atoms, two or more atoms together. They just happen to be two atoms that are the same element. Now, you may be asking, so what about something, say, like water? Our good friend H2O. Water is this guy. Water is a molecule because it meets the basic definition of a molecule. It is two or more atoms that are bound together, basically. Water is also a compound. So you may be asking yourself, what's the difference between, say, a compound and an element or a compound and a molecule? A compound is atoms of two or more elements. So a compound is something that is two or more elements. Here in water, we have hydrogen and oxygen, which means this is also a compound. It's a molecule, it's a compound water. It is not an element because it's not, there are different elements involved. So water is a molecule or a compound. Now, H2 is an element or a molecule, but it is not a compound because there's not different elements involved. So again, that's a slight difference where sometimes people get confused about like, hey, what's really the difference between, say, a compound, a molecule, or an element? And that's the difference. So an element is basically, much like it sounds like, all atoms from the same element. And that can be either, it could be a molecule, which means we have two hydrogens, two oxygens, they're all the same. Water can be a molecule because it also, again, meets that definition of just basically two atoms together or two or more atoms, but it can be a compound as well because it's two or more elements that are together. But water definitely cannot be a element because, again, oxygen, hydrogen are different ones. Any questions on that there? So when we do write formulas, right, in chemistry, we oftentimes will use sort of formulas there. And for example, looking at water, H2O, we use subscripts to indicate how many atoms of that particular element are there. The subscript always goes to the guy to the left of it. So this would tell us that we have two hydrogen atoms. And pretty much in chemistry, if there is nothing written there, it basically means that there is one there. So there would be one atom of water. O2 means that there are two oxygen atoms in there. H2, as we saw, means that there are two hydrogen atoms. If you had hydrogen peroxide, H2O2, that would be two hydrogens and two oxygens that are basically involved. Now, other important things obviously are chemical reactions. In chemical reactions, it involves really a chemical change. So when we do sort of chemical reactions, These guys basically involve what are referred to as a chemical change. What is a chemical change? Well, a chemical change is basically what you start with and what you end with. These things are fundamentally different. And one important part of that is you cannot get back whatever you started with by any type of physical means like boiling, freezing, melting, any of those type of things. So what you start with fundamentally changes to something that's very different. And that's different than a physical change where what you start with and what you end with are basically the same thing. May just look different. So for example, what we were talking about earlier when we were talking about the ice cube, as we take an ice cube from solid and then melt it to liquid water, take the liquid water and melt and evaporate it to steam, ice, liquid water, and steam, they're all fundamentally still H2O. They're all still fundamentally water. They may just look different. Obviously, an ice cube looks different than liquid water. Obviously, steam looks different than liquid water. But they're still all fundamentally still H2O. And that's why that's referred to as a physical change. A chemical change involves a chemical reaction. If, for example, we take water, like it shows here in this picture, and we run an electrical current over it, we can actually produce basically hydrogen gas and oxygen gas, like what we have over here. We got some O2 and some H2 being formed from our water molecules. You do what you like with those things, oxygen, hydrogen, you're not going to get the water back by any type of physical means, putting it in the freezer or anything like that. You need to do a chemical change to get it back as well. So in a chemical sort of change or a chemical reaction, which is a lot of what we look at here, we can take compounds like this back to its elements, right? Like what we have over here. Remember that once we hit elements, that is pretty much as far back as you could go. So, I mean, that's pretty much it. Once you hit the elements, you can't really break those things down into anything else. Any questions on sort of that little overview there of some of the stuff that obviously we will go into more detail in some other chapters as well. Okay, then let's talk a little bit about the scientific method for just a little bit. And really the scientific method is sort of the steps that you take, when you really, it all begins by observing something, really. An observation is really, what really sets that off is observing something. So usually in sort of the scientific method, we sort of make some type of observation and it piques some curiosity there. And we try to figure out, what is going on to make what we just saw occur. And it involves perhaps making a hypothesis, which is sort of a testable sort of theory of what's going on to try to help us explain. It involves obviously experimentation to sort of test our hypothesis and stuff like that. So let's take a look at some of those steps here. Again, it really does all sort of start with that observation. When we do that observation, again, we sort of formulate this testable sort of explanation for what we observed. We obviously would then try to test our hypothesis. And sometimes what ends up happening is we make some new observations, which leads to revisions of our hypothesis and more experimentation. And you sort of go around in the circle, could go around a very long time, if it's a lot of things happening. But at some point, a couple of things sort of happen. You sort of come up with, at some point, sort of a theory. And a theory is sort of a model that tries to explain, sort of these observations that you're seeing as you're doing these experimentations. Now, the difference with a theory is a model that, it can be sort of modified, if you will. So it may not always be found to be sort of correct in all aspects. And we're going to see some here in just a bit, some theories that, are correct in, certain cases, not so correct in all aspects. Later experiments maybe has shown, maybe this part of this theory is not right, but this part is right. So you get this sort of theory where you make sort of predictions, use some more experiments. And again, the difference here between a theory where you can sort of modify it, and maybe it's been shown that later it's not correct in all aspects, and something like a law is something that really is sort of, I guess you could say, sort of certain in that sense, that, it always occurs that way, no matter what happens. There's kind of no revision of what happens. Like the law of conservation of mass. Mass is always conserved. Law of conservation of energy. Energy is always conserved, and stuff like that. Something like Dalton's atomic theory, as we'll talk about, correct in certain aspects, later found not to be correct in other aspects. Bohr's theory of the hydrogen atom, as we'll also talk about, correct in certain cases, works really well for hydrogen, but as you move away from hydrogen, it doesn't work as well. So, a theory is really a sort of a predictive type model that tries to explain what you're seeing. Maybe not correct in all aspects, maybe will be found to be later, disproven in some aspects. And again, that's different than our law, which really does summarize what happens. It always sort of happens that way, no matter sort of what the situation is. And again, a hypothesis is an important part of all that. And the important part about a hypothesis is it does usually need to be some type of testable type of sort of theory about what you're sort of seeing and explaining, and that you can go and sort of do these experiments to try to figure out, is your hypothesis sort of correct? Are you on the right path, and stuff like that. Any questions on sort of the scientific method there? All right. So then we're now going to kind of talk about some leading into sort of the atom and some ideas of, some laws and theories and what happens, sort of what's happening with sort of how we get to our modern version of the atom. So Greeks, it all came back or started a long time ago. They thought about sort of matter and nature as these sort of indestructible sort of things they called atomoses, which was sort of our forerunner to atoms, as we'll talk about. And a lot of work was done, obviously, in early years, trying to sort of understand really the nature of the atom. Several elements were discovered. Robert Boyle was sort of considered the first chemist. He did a lot of quantitative experiments. Quantitative means that, involves numbers, values, calculations. Again, a lot of this work allowed some early sort of laws to sort of come about. And remember, laws are really these things that, are sort of definites, if you will, again, won't really change. Some important laws, that we sort of come across is, again, the law of conservation of mass. Mass is neither created nor destroyed. Also, the law of definite proportions. A given compound always contains the exact same proportion of elements by mass. What does that mean? For example, if you look at something, say, like water, which is H2O, no matter where you get your water from, what bottle it's in, I suppose, water fundamentally, if you're just looking at the water part, is always 2 hydrogen atoms for every 1 oxygen atom, which means by mass, hydrogen is about 1 gram. So it's really kind of 2 grams of hydrogen for every kind of 16 grams of oxygen that are there, which means no matter kind of where you get your water from, you're really dealing with like 1 gram of hydrogen for every 8 grams of oxygen that are involved. And again, fundamentally, water, when it comes together, will always come together in that sort of proportion of 2 hydrogens for every 1 oxygen atom, which always gives you by mass that sort of 1 gram of hydrogen to 8 grams of oxygen that you sort of produce when you do make water. Another important sort of law was one by Dalton. It's a law of multiple proportions. And basically what he said was that when we take basically 2 elements to form a compound, the ratio of the mass of the second element that combines with 1 gram of the first one can always be reduced to sort of its smallest whole numbers. So basically what he's saying is that when these elements come together, they come together in basically whole number ratios, if you will. You really don't get like a half of atom of, say, carbon to a half of atom of oxygen. So if you look at just carbon and oxygen, for example, you could have a carbon and an oxygen that comes together that makes carbon monoxide, and they come together in this proportion of 1 carbon atom to 1 oxygen atom. You could also take carbon and oxygen where they come together in CO2, makes carbon dioxide, comes together in basically 1 carbon atom for every 2 oxygen atoms. In that case, kind of whole numbers. You'll never have it, where you get like a half of like carbon atom comes together with like a half of oxygen atom and stuff like that. So you'll never get that sort of ratio. They always come together in these proportions. And as we'll talk a little bit about, kind of here, and when we talk about nomenclature and naming, they do come together in the simplest ratio of sort of those whole numbers, especially when we talk about, for example, sort of a metal and a non-metal, like a cation and an anion, like sodium chloride, always comes together in the simplest ratio of those guys. We take something like calcium and chloride, they come together as CaCl2. Simplest ratio that basically gets everybody to 0 charge is you need 2 of those chlorides to balance out the 1 calcium. So they always come together in these simplest whole number ratios, which is essentially what is sometimes referred to as the empirical formula, as we'll talk about a little bit later in the chapter. So now we're going to get into some of these experiments that really sort of led to an understanding of what we see with sort of the modern atom and how we get to sort of the modern structure for the atom. And a lot of experiments were done, but early on, a guy by the name of Dalton, John Dalton here, this picture of him right there. He was an interesting guy. He basically kept the weather records every day. So he'd write down what the weather was outside. He never married, surprisingly. But he did like to go bowling on Thursday, which, it's a really important piece of information and will show up on exams. So I know you're thinking I'm kidding, but I'm not kidding. So when you see that question, go with Thursday. Although I do like the other choices, like Monday's a day that ends in Y, Cosmic Bowling Fridays, but it was Thursday. But really, he wasn't a really good lecturer. He wasn't a really good public speaker. But what he was able to do was sort of come up with what is sometimes referred to, obviously, as Dalton's atomic theory. And this is sort of a theory that sort of definition of what we sort of determine as atoms. So a sort of precise definition of atoms, what he felt was important in terms of, what makes up an atom. And first off, the first sort of major part of it was that each element is made up of these tiny, indestructible sort of particles that are called atoms. And that is true. They are made up of these tiny particles that are called atoms. He also said that atoms of a given element are identical, and atoms of different elements are different in some fundamental way. So if you had an iron atom versus a copper atom, they would have some different sort of properties associated with it. He also said that chemical compounds are formed when different atoms combine to each other. Again, in these sort of whole number ratios when they do come together. And that chemical reactions involve rearranging really the atoms, the way they're bound together. The atoms themselves are not changed, and that basis is really true. If you think about sort of the idea of, as you may be familiar with, when you balance an equation, right? When you balance a chemical equation, if you started with 4 carbon atoms, you should end with 4 carbon atoms. They may be in different sort of compounds on the product side from where they started on the reactant side, but you don't lose anything along the way. You wouldn't lose sort of, 4 carbons, they wouldn't just disappear. They would still be there, may not be there in the 100%. Now, this is Dalton's atomic theory, and you do need to know these different parts of it. But there's a couple of parts of it that, because it is a theory, was found to be not correct in all aspects. So as we were just talking about a second ago, remember, a theory is sort of an explanation of what's going on, but it may be found or may be revised or found maybe not to be correct in all fashions. So you do need to know these points, but a couple of points where maybe it's not 100% correct. It's this idea of these guys being indestructible. Now, when we think about in normal chemical reactions, for example, the elements and these atoms basically remain. They're there when you start and when you end. Reactants to products, we have the same number of carbons that we start with and end with. But in sort of nuclear reactions, for example, which we don't talk about in this class, but you will talk about in 200B, in nuclear reactions, we actually don't have that conservation of elements. You could actually change one element into another one by basically shooting it with some particles like neutrons, alpha particles, some type of radioactive type particles. So that's one aspect of his theory that's not correct in every way. The other part of it is this part of it where it says that atoms of a given element are identical. The existence of what are known as isotopes basically sort of disproves that part of the theory. And what an isotope is basically the same element, but has a different mass. So isotopes are basically the same element with different masses, or different mass. And right there, obviously, if they are obviously the same element but have different masses, then they cannot obviously be identical to each other. So Dalton's atomic theory, not correct in 100% of all aspects of it, just like we were just talking about that, theories are not 100% correct. And those are the two main parts that are sort of where it lacks, if you will, in being correct. Any questions on that? Okay, so why don't you take a second here and think about this question, and let's read it carefully because I think it's kind of a double negative maybe. Which of the following statements regarding Dalton's atomic theory are still believed to be true? So which ones are still believed to be true? So take a moment and think about it there. Okay, so since we just talked about it here, elements are made of tiny particles called atoms, so that is true. They are definitely made up of tiny particles, which are called atoms. As we'll talk about, that's basically where our protons, electrons, and neutrons are. All atoms of a given element are identical, so as we just talked about, that part is not true because, again, the existence of those isotopes, which are the same elements but have different masses, obviously means that they are not identical to each other. A given compound always has the same relative number and types of atoms, and that is true. Again, as we talked about with water, no matter where you get your water, you're always going to have the kind of 2 hydrogen to 1 oxygen sort of arrangement. And atoms are indestructible. Again, as we talked about with sort of those kind of nuclear reactions, you actually can sort of change the element along. So number 1 and number 3 here of Dalton's atomic theory are still correct. And again, the other two, not really correct in all aspects. Any questions on Dalton's atomic theory there? Now, there's other theories and sort of ideas that we're going to talk about in some later chapters, some of which deals with gases, for example. So Guy Lussac's and Avogadro basically had some gas laws. Guy Lussac's law measured basically the pressure and temperature relationship of a gas as basically volume was held constant. And what you basically saw, and we'll talk more about it when we get to the sort of the gas chapter, is as the pressure goes up, so does the temperature. And as the pressure goes down, so does the temperature. So if you just think about sort of, how they're able to react with each other and how we sort of know that there's a lot of reaction going on is by pressure, right? So in order for gas molecules, as they're flying around, they have to collide with each other, collide with the container. That's going to cause a lot of pressure, and that would indicate a lot of reaction going on. So when we have a lot more temperature, a high temperature, a lot more gas molecules are flying around. That's going to increase the collisions between the gas molecules, can cause more reactions really to take place. And the result of that is we would have probably more gas, more pressure. And we see that sort of direct relationship. As the temperature increases, so does the pressure. Opposite is true. If we kind of lower the temperature, everybody's going to be flying around a lot slower, which means it's going to take longer for those guys to come in contact with other ones. And it's going to result in probably less collisions, going to result in our pressure dropping down. So what we'll see here is, again, the pressure start to decrease as the temperature decreases. Now, Avogadro, as you may remember Avogadro's number, he also had a gas law, as we'll talk about as well. And he dealt with kind of constant pressure and temperature. What we see is the volume of a gas is proportional to the moles of the gas. So the volume of a gas is kind of proportional. That's what that little symbol means, to the moles of a gas. Which means, as we'll talk about actually when we do get into sort of the gas chapter, you could do stoichiometry. Typically, we do it with a mole to mole relationship. I could also do stoichiometry kind of with a volume to volume relationship under these sort of conditions of Avogadro's number. And what we see is as the volume of gas increases, so does the number of moles. And that's sort of what we see here. 2 volumes of hydrogen combines with 1 volume of oxygen. And again, we'll talk more about this when we get into gases in that chapter, but you could kind of look at it like this as a relationship of moles to volumes. This is sort of how Dalton sort of pictured the combination of different elements when they come together. Here in this example, we have basically 3 different compounds that are formed, although they are all formed basically from the same 2 elements. They basically both contain nitrogen and oxygen. But again, the different arrangement of even the same elements, the different amounts of these different elements does give us different sort of compounds, which obviously they do have different properties as well, and a different sort of proportion of nitrogen to oxygen, kind of a 1-to-1 relationship in the first guy, a 1 nitrogen to 2 oxygen in the second, and then a 2 nitrogen to 1 oxygen in the last one, giving us some different sort of gas molecules here: nitrogen monoxide, nitrogen dioxide, and dinitrogen monoxide there in the last one. So Dalton's sort of theory was really good. It was a nice sort of building block of understanding really the atom and so forth. And really based on Dalton's atomic theory, the atom is really defined as that basic unit of an element that could come into basically chemical combination. There was a lot of experiments that were done leading up to sort of some major sort of breakthroughs, if you will, or experiments that helped us understand sort of the atom and where it can, how it's basically put together. And that's what we're going to kind of talk about now is sort of, the discovery of the major parts of an atom. And the major parts of the atom is, although atoms are extremely small sort of particles, if you will, they are really made up of even smaller particles, which are referred to as subatomic particles. And subatomic particles are basically three of ones which you probably are familiar with: electrons, protons, and neutrons. So just a reminder that when we talk about electrons, those are negatively charged particles. Our protons are positively charged particles, and our neutrons have no charge. So what we're going to talk about now is really the investigation and some of the important experiments that help us understand sort of some properties of these different subatomic particles, sort of where they are in the atom as a result of these experiments. And really the first one that we're going to look at, and some of the first couple of experiments that we're going to look at, are really involving sort of the discovery really of electrons. And the discovery of electrons really all came about by what is sometimes referred to as the CRT tube. That's the cathode ray tube. And that's basically, as we'll see in just a second, basically a tube that shoots kind of electrons, basically negatively charged particles. And this was very big sort of help in understanding sort of the nature of electrons and some of the properties of electrons. And that all really started with a guy by the name of Thomson. So J.J. Thomson did a lot of work with the cathode ray tube. And it brings up a really important sort of concept in chemistry, as you may be familiar with or not. But it's kind of like what is sometimes referred to as opposites attract, right? So much like in life, if you have two negative people, they don't really want to be around each other. Two positive people, too cheerful, don't really want to be around each other either. So if you get to make a positive person, negative person, sort of balances each other out. And the same thing happens sort of in chemistry, if you will. Anything that has the same charge will repel one another. They don't want to be near each other. But things that have opposite charge are attracted to one another. And that is what is sometimes referred to as electrostatic attraction. And so if you have a positive guy, they're going to kind of want to go away from each other. If you have a negatively charged guy and a negatively charged guy, they're going to want to go away from each other. But if you have a positive charged guy and a negatively charged guy, they would want to be attracted to each other. So the basis of what a CRT tube kind of is it kind of has like an electrical field. It kind of has a negative side and it has a positive side in this tube. And when we shoot something like electrons, which are negatively charged, they're going to kind of go away from the negative side and be attracted towards the positive side of the CRT tube. So it's going to basically be shooting this way. And the major outcome that came from Thomson, which you do need to know, is he was able to determine the charge to mass of an electron by doing these experiments. So by doing these experiments, he was able to come up with the charge to mass of an electron. And the atom must also contain positively particles to balance out the negative particles that we know that are electrons. So there's always this belief that, okay, we've now discovered that, there are these negatively charged sort of particles, but the atom is believed to be sort of overall neutral. So there must be something positive to balance out these electrons. And we'll get into that in just a second of what that is. Here's a sort of a picture of an actual CRT tube, a cathode ray tube. You may be familiar with it. If if you've ever seen maybe an older TV where it kind of has like the big back, not like a flat screen, but in the back of the TV, this big sort of back that used to be really boxy, are computer monitors. If older computer monitors that used to have these big backs in it, and those were CRT sort of monitors and TVs, kind of the picture tube in there. But basically, as you can see here, there's a metal in here that is a negatively sort of charged. There's a metal that's positively charged. And basically that stream of negative particles, which are later found to be electrons, would be heading towards the positive side here. A lot of times they would put something on this side of the tube that would sort of fluoresce. So as the electrons would hit it, you would kind of see it basically light up as they're kind of shooting the electrons, you know, at the tube there. Now, the importance of sort of Thomson's experiment, as I mentioned before, was that he was able to, and by the way, there's Thomson right there staring at his tube, and he was able to come up with the charge to mass of an electron, and it's this number right here, which is minus 1.76 times 10 to the 8 coulombs per gram. Coulombs is a unit of electrical charge, so that's why I say charge to grams, which is a mass, so charge to mass of an electron. So Thomson did an experiment with CRT tubes, and he was able to determine for an electron the charge to mass of an electron. And again, that's sort of what you need to know for Thomson's experiment. And that led really good into the next kind of important experiment, especially in terms of an electron. And that was one that was done by Milligan. And Milligan basically did what is referred to as the oil drop experiment. And in the oil drop experiment, much like the name implies, he took basically charged oil drops and he basically put it into a chamber where he had like an electrical field, kind of like a positive guy and a negative guy. He dropped these oil droplets in there and then kind of turned on the electrical field. And what he was able to do was he was able to adjust the electrical field in such a way that basically the oil droplet basically just kind of hung there. It wouldn't fall, it wouldn't go up, it wouldn't go down. It was just able to sort of suspended there. And again, as he kind of shot it into the container, it gained a charge, a natural charge from sort of dropping, and it was able to really sort of adjust that electrical field in such a way that the droplet would not move. And what he was able to basically figure out from this experiment was the charge on an electron. So he was able to figure out the charge on an electron here. So why is this important? Well, this is important in combination with Thomson's experiment. So if you remember, Thomson's experiment basically figured out the charge to mass of an electron. Milligan's experiment able to figure out the charge of an electron. So if you take both of those values basically and you divide what Thomson had, the charge of an electron would cancel out. And from those two important experiments, the mass of an actual electron was able to be determined. And the mass of the electron was able to be determined by using the charge that he found. And by the way, the charge he found there was minus 1.6 times 10 to the minus 9 coulombs. Here's a prettier picture of what I drew there. So this is sort of the chamber. Basically, the oil droplets would go in there, little hole, and again, those droplets would kind of come through. And again, he was able to adjust really the sort of electrical field in such a way and stop that oil droplet from basically dropping. And again, using the charge on an electron and dividing it by the charge to mass, the mass of an electron was able to be determined. This coming from Milligan's experiment and the oil drop experiment. This coming from Thomson's experiment. And the CRT tubes, and the mass of an electron again being able to be determined. And if we do that calculation here on this page, we do see that the mass of an electron is 9.09 times 10 to the minus 28 grams. That is a very small number. Minus 28 means you are taking this decimal and going 28 places to the left and adding zeros. So it's a very, very small sort of number. Any questions on those things there? So to reiterate what you need to know, again, you need to know that Thomson did experiments using the CRT tube. From his experiments, he was able to determine the charge to mass of an electron. You then need to know it was sort of followed up by Milligan, who did the oil drop experiment, and a little bit about what the experiment was. And that from that experiment, he was able to determine the charge on an electron. And again, using sort of the results of both of those experiments, we're able to determine the mass of an electron, which is 9.09 times 10 to the minus 28. Any questions on that so far? Now, if we think about our atom, which as we earlier talked about is basically made up of protons, neutrons, and electrons, we just took care of electrons and sort of its discovery and some of the properties of electrons. So as was just mentioned earlier and was also thought of, that, you know, it was believed that obviously the atoms do contain electrons, but there has to be something else in the atom that sort of balances out that negative charge from the electrons. And that's where it takes us now to the proton and the nucleus and sort of the experiments that helped us understand sort of how they came about, if you will. So as I mentioned before, it was definitely believed that the atom was electrically neutral. It definitely contained these negatively charged electrons and had to have something positive along the way there to balance them out. So, and a very early sort of idea of what the atom was and what it sort of was sort of made up of and how it looked was one that was proposed by Thomson. And it's sometimes referred to as the plum pudding model of the atom. And basically what he said was, we have an atom, and basically this atom, because it does need to have something that's positively charged to balance out everything, it's basically a sphere of positive charge. So all this blue would be this positive charge that's basically spread out all over the sphere. Positive charge. And basically what he said was, embedded inside of this positive sphere was these negatively charged electrons. So you got these negatively charged electrons embedded inside the atom, kind of like the raisins in the plum pudding, basically is what it is, kind of a pudding with raisins in it. You thought the raisins looked like the electrons, the pudding was like the positive charge of the atom. And he said that most of the mass of the atom was the electrons. So this was sort of the early belief of basically the model of the atom, basically this kind of smear of positive charge spread out over the sphere, and these kind of electrons that are embedded inside of it, making up pretty much the majority of the mass of the atom. Looks almost like what I drew there. And basically this was sort of the model of the atom that people were kind of going by and going on. And they continued with this sort of idea of this atom and this sort of structure of the atom until really the next really important sort of experiment that occurred. And that is one that occurred by a guy named Rutherford, along with some other guys, Geiger from like the Geiger counter and so forth. And Rutherford did what is referred to as the gold foil experiment. And the gold foil experiment was a really important experiment. He basically took some radioactive particles, and there's kind of three major radioactive particles that we oftentimes come across. There's alpha particles, and these are basically positively charged particles. They're basically helium nucleuses. There's beta particles. These are negatively charged particles, kind of like electrons. And there's gamma particles. or gamma rays actually. And these guys have like no charge. So for the most part, these are kind of like, protons, electrons, and neutrons, basically, kind of in that sense. And because these guys are sort of positively charged, negatively charged, have no charge, when we're dealing with particles that have some type of charge associated with them, we could use something like an electrical field to really determine what is the charge is going on. So for example, if we built like an electrical field, like a negatively charged side and a positively charged side, and we shot particles kind of through this electrical field, if we shot a particle through this and we saw that the particle started to sort of bend upwards, if you will, what we would know about that particle is it bent towards the positive side. And remember that opposites attract, which means we can make a pretty good guess that this particle is probably negatively charged. That's why it kind of bent away from the negative charge and up towards the positive charge. If we shot a particle and it did kind of the opposite and bended towards the negatively charged part of the electrical field, we can make a pretty safe assumption that that particle is probably positively charged. Again, going to be attracted to the negative side of the electrical field, and obviously move away from the positive side of the field as well. Now, if we shot a particle through this electrical field, and it just basically went kind of straight through, we could probably assume that this guy had no charge. It's not going to be attracted to the positive or negative or repelled by the positive or negative because it basically has no charge. And using sort of that information, it helped Rutherford sort of do an experiment. And basically what he did was he took these little pieces of gold and other metals, which are basically atoms, and he shot alpha particles at it. So he shot these alpha particles at it. And he was going off of the assumption of sort of the plum pudding model that we saw here in this guy. And what he expected to happen was when he shot these alpha particles that are positively charged, they're heavy, they're moving pretty fast, that, you would expect it to probably go through with some deflection, a little bit of deflection, right? Kind of come through with a little bit of deflection sort of happening. It's kind of like if you took a big, just like one sheet of paper and you held both sides of the paper really tight, and somebody took like a pen and you pushed the pen through the paper. It probably would go through the paper, but maybe deflect a little bit as it went through because you kind of threw the pen really hard at it, you held the paper really tight, and it kind of went through. Because if the paper was sort of our positive charge spread out all over, and I did that, it's going to poke through and kind of deflect a little bit. And that's sort of what they expected to happen when they did this experiment. And they were kind of surprised because what they actually saw happen when they shot these positive particles at these pieces of gold foil and other metals was that they saw pretty much the alpha particles sailed right through with no problem, and just kind of went right through no problem, which was very sort of surprising to them because based on sort of the plum pudding model, as I just mentioned, they really did expect most of the particles to have some deflection because it's going through this really positive spread out sort of area. But what they found is, as we can see here in a much better picture of so what's happening, that's this radioactive source shooting these alpha particles at pieces of gold foil and other metals. But what they saw was pretty much most of them just sailed through no problem. They have this little detector kind of guy back here so they can see where the particles are hitting. And most of them pretty much, as you can see, kind of the strongest beam heading straight through, no problem, right on through. But what they saw, which was kind of surprising to them, was every now and then they would see a particle get bounced off at these kind of large angles. They would even see some particles kind of head back towards the source at which they basically came from. So that's very different than what happened with a majority of the particles that went through with no problem, just kind of sailed right through. So what did that sort of mean when they kind of witnessed what happened here, that, you know, for the most part, we had all these particles go right through, no deflection or anything. That means that when those particles went right through and didn't hit anything, and hit nothing here, that means that they probably went through empty space, right? Had no problem, sailed right through, nothing in its way, probably went through a lot of empty space. But what accounted for these particles bouncing off at these really big angles, right? Or even coming back at the source? Well, what we know is the alpha particles are positively charged. That means that it did have to hit something that was very, very positively charged in order to make those particles bounce off at those really far angles. It had to be something that was very, very densely positively charged. So if you think about my paper example, we took just a sheet of paper all by itself, nothing done with it, held it both, and you shot your pen through it, it would bounce through. If you took that same piece of paper and you just kept folding it and folding it and folding it till you have this little small square of paper that's left, right? Then if you try to poke a pen through a paper that's been folded into a small square, what you would see is you would actually throw it at the paper, it would bounce off, right? It would really bounce off at sort of a long, long area. And this is basically what they observed, that it had to be something that was very, very positive to make those alpha particles bounce off at those large angles. So this really did throw sort of a wrench into the plum pudding model. They expected pretty much everybody to have some type of deflection, but they actually didn't see that. They actually saw most of them went through no problem, which meant that they hit pretty much empty space. But those guys that got bounced off at really large angles hit this really positive core, which, as we'll talk about here in a second, is pretty much what we call now the nucleus. So what this meant was Rutherford had to pretty much say, not so correct, the plum pudding model, and sort of abandon that model and come up with sort of a new model of the atom, kind of like the current model of the atom, if you will. And he basically said that the atom is mostly empty space, which is what accounts for those alpha particles just sailing through, no problem. They pretty much didn't hit anything. He also was able to say that it must contain a very dense, positively charged core, which is known as the nucleus. And as we know, and as we'll talk about later, found that that is pretty much where we have our positively charged protons, and much later found that that's where our neutrons are held in like 1930s. That is where our neutrons were found basically to be there. Electrons are traveling about this empty space. So this empty space is pretty much where our electrons are traveling. And most of the mass of the atom is actually not the electrons, but it's actually the nucleus where we find protons and neutrons. So remember that in the plum pudding model, most of the mass of the atom was found to be the electrons. Here, most of the mass of the atom is basically in the nucleus where our protons and neutrons are found. So abandoning sort of the plum pudding model for really the modern day model of the atom, we have our nucleus, which has protons, again, later found to also contain neutrons, and traveling around in this sort of empty space in random pattern is where we have our electrons. As we'll also talk about again, as you may know, electrons do not travel in pretty circles. They do travel pretty randomly about the nucleus at some point. There is some attraction though. So if we think about it, right, our nucleus is pretty much positively charged, our electrons are negatively charged. So we do get some of that electrostatic attraction between the electrons and the protons there because of that differences in the charge. Also, depending on how far your electrons are from the nucleus as to whether or not they're involved in things like bonding and stuff like that, which we'll talk about in later chapters. So a couple of things. Again, you do need to know Rutherford's experiment. You do need to know that he shot alpha particles at pieces of gold foil and other metals. You do need to know that he believed that what the plum pudding model was the correct model, and you need to know what the plum pudding model of the atom is. You need to know what happened when he shot the alpha particles at those pieces of gold foil. That most went through, some were deflected at large angles, and you need to know basically that that meant that the plum pudding model, not so good, and that the current model of the atom is that it's mostly empty space, has a positively charged nucleus, which contains protons and neutrons, and electrons are traveling out at a large distance or a distance from the nucleus, and most of the mass of the atom is the nucleus. Any questions on what you need to know? Now, again, this table here sort of summarizes pretty much what we just talked about in those different experiments, from our sort of discovery of electrons to, again, sort of our Rutherford experiment and our plum pudding model here. So these positively charged core was later found to be protons, and protons has a mass of 1.67252 times 10 to the minus 24 grams. And if we compare that to an electron's mass that we saw earlier, which is 9.09 times 10 to the minus 28 grams, this guy right here is about 1840 times heavier than an electron. By the way, when you look at an exponent, negative 24 means you're only going 24 places to the left. Negative 28 means you're going 28 places to the left and putting zeros. So when you have a negative exponent, the smaller negative number is the larger number. And that's why that's the larger number there up on top, which is our protons. So what does that mean? Well, that really does sort of lend to what Rutherford said, which was, no, the mass of the atom, the most mass of the atom is actually the nucleus. And because the nucleus has protons, which each proton is about 1840 times heavier than an electron, that makes sense that most of the mass of the atom is actually the nucleus, where the protons are basically hanging out. Now, at this stage, when we think about sort of the atom, it is basically some of these important things here. It is obviously very small. The nucleus is very small compared to the volume of the actual atom. You could think about the atom as being like a football stadium, and like the nucleus, like there on the 50-yard line, is sort of the what the nucleus sort of is. There's also a really important idea, which was, all right, we now know that atoms contain protons, which are positively charged. We also know that atoms contain electrons, which are negatively charged. But it was a long-held sort of belief that in addition to those two subatomic particles, that there actually was sort of a third particle or subatomic particle present. And it wasn't until about 1932 that a guy by the name of Chadwick was doing a lot of experiments with radioactivity and things that really resembled X-rays. So X-rays are kind of neutral. And basically, some experiments that he did showed that the existence of this third particle, which are known as neutrons, and it had a mass of 1.67495. You may be wondering, why did they take it out so many digits? They take it out so many digits because if we look at the number for our proton, which was like 1.67252 times 10 to the minus 24 grams. If we compare this number to this number here, we see that actually the neutron is the heaviest of all three particles, just barely. Out there to like the third decimal place is just barely the heaviest. So actually the neutron is the heaviest of all three particles, followed very closely by the proton. And then way down on the road there is our electron, which again is 9.09 times 10 to the minus 28 grams in terms of its mass. So now if we think about it, well, the neutron is as well is about 1,800 times heavier than an electron. Proton also 1,800 times heavier than an electron. And if we think about the nucleus of the atom, which has our protons and our neutrons, again, makes sense what Rutherford said, that most of the mass of the atom is the nucleus, which contains both protons and neutrons, which are much, much heavier than any electron that's basically flying around in that empty space. Any questions on that there? So here's just a table of it. And to be truthfully honest with you, you don't have to memorize these numbers. You do need to know that in terms of mass, neutron is the heaviest, kind of followed by the proton, and lastly, the electron would be the lightest of the three. You don't actually have to know the numbers. Truthfully, they might even be provided for you somewhere along the way there. You do need to know sort of the order, if you will, that neutron the heaviest, proton then the electron much, much lighter than either of those two. Any questions on those there? And again, just for location purposes, obviously, you do need to know the modern version of the atom. Again, electrons in that empty space moving around randomly from the nucleus, protons and neutrons found in the nucleus, and protons have a +1 charge, electrons -1 charge, and obviously neutrons have no charge. So the nucleus is small compared, again, to the overall size of the atom. It's extremely dense, the nucleus accounts for, again, as we talked about, pretty much most of the mass of that atom. Here's sort of a cross section of it. You can see, again, very, very small area where our nucleus is, where our protons and neutrons are. This kind of pinkish area, if you will, if it's coming up on your screen, is where our electrons are basically traveling about in this sort of random motion. You oftentimes will see these sort of pictures where you see this kind of pinkish color, some type of color, and it may be hard to pick up here, but if you look closest to the nucleus is much darker. And then as you kind of come out from the nucleus, it gets obviously lighter and lighter in terms of the color of pink. And that's sometimes what is referred to as an electron density map. An electron density map basically is an area where we see electrons, and the kind of darker areas is where we see a heavier amount, or a higher probability, I guess is a better way of saying it, a higher probability of finding an electron in an atom. Kind of the lighter color is a lower probability of finding an electron. And what we see is near the nucleus, a much darker color, which is a higher probability of finding an electron, which makes sense. Again, electrons being negative, nucleus being positive. So we would expect a sort of higher concentration, or again, not concentration, wrong word there, a higher probability of finding an electron near the nucleus. That probability gets much smaller as we move further away from the nucleus. There's a lesser of a probability of finding that electron. Any questions on that there? Okay, I think what we're going to do, we're going to lay up the lecturing part now. We're almost actually done with chapter 1, so we'll save some for tomorrow to continue on. But I did want to talk about a little bit about some of the lab stuff here for a little bit of the rest of the time. But before we do, any questions on anything we sort of lecture?